Okay, welcome everyone. My name is Bart Verhagen. I am a consultant in computer vision and mainly occupied with writing C++. So in this talk, we're going to talk about things I learned from the static analyzer. So it's really going to be about rather the low-hanging fruit, the easy kind of things that static code analyzers typically point out to you, but that are actually very useful to have as a kind of a habit while you're coding. So some things that are really worth to be put into your muscle memory and to actually, by default, just use it straight away. So this is not going to be a talk about with the big C++ paradigm shifts. This is really going to be a rather easy, relaxed session about things. Many of you probably already know things, but I hope that I can convince you to start using it, because apparently there's quite a large gap in between those two. And even if you're not using a static code analyzer today, I hope it will still be useful for you in order to start using them and to get them actually into your muscle memory. When we want to base these kind of things on the suggestions that a static code analyzer actually makes, let's first take a look at what kind of suggestions a static code analyzer can make today. And first of all, it's kind of a cooperation basically between a developer and a static code analyzer that's going on here, where the developer is basically very good at high-level stuff. He or she knows his application or library very well and what it's supposed to do, and in addition, it typically knows its components and how they are or should be connected to each other. So the developer is rather good at that. Unfortunately, they're not that good actually at the more of the low-level details. As I'm talking about really the itty-nitty details that can be in the C++ library, in addition to a lot of places where there is actually undefined behavior. And just to illustrate this point, there are a couple of talks about some of which are from Bjarne Stroustrup himself, and when he actually talks about how many people there are in the world that actually know and understand the complete C++ standard, then his conclusion is that it's actually only a very few people, and if you have to take Bjarne Stroustrup on his word, then it's basically no one that understands the full C++ standard. Luckily, once we start actually going to tools, it's not anymore one developer that needs to know the entire C++ library, but we can basically build on a community of developers that together actually try to get a tool that actually represents the C++ library and its standard rather well. Of course, it's also only a tool. There are limits, so it's definitely not the case that the standard library is perfectly in there, but nevertheless it is probably already getting quite a lot more of all those itty-nitty little details that are in the C++ standard, including sometimes it are corners, in order to understand them and to actually point them out to you. On the other hand, today static code analyzers are definitely getting smarter and smarter and creeping up into a higher level of abstraction, but still today they are definitely not at the level of where a developer can actually think about abstract concepts and how they are all interconnected. When we then take a look at the kind of suggestions a static code analyzer typically gives, and we make a union with the subjects that I'm going to touch on today, then we see that there are actually four focus areas where we will look at today. First of all, there's consistency. So static code analyzers, they can kind of help us with making our codes more consistent. And just to illustrate how important consistency can be, there are actually, in most companies that I encounter, there's actually like this rather strict coding guidelines on how to use C++ well and how to not use it. And sometimes there's kind of this holy power even to which everything has to comply. Static code analyzers, they typically do not give that kind of information, although some actually have implemented the widely used ones. But it will, in addition to this kind of coding guidelines, will give a couple of additional consistency remarks to make your code more consistent. The idea behind this consistency is that more consistent code will actually lead to less surprises and therefore to actually better code and less bugs. Then there is maintenance. Still today, it's actually the most significant cost in a software project, but it's quite often overlooked actually by the developers themselves. Even though we're actually spending a lot of time in it, for example, if we try to add a new feature, then typically we are spending more time in refactoring our code to be able to enable that feature than really in implementing the actual feature. And so there we see that just having better maintainable code is actually also an important goal to keep in mind. Then there is performance. Static code analyzers definitely sometimes give suggestions on performance. Of course, they are rather conservative in this respect. So that means that they will typically only give this kind of suggestions when they are rather sure that in all circumstances, or in almost all circumstances, their suggestion will actually be faster than the current code that they are looking at today. And then the fourth one is probably the one where static code analyzers are more widely known for and are used for today, and that's probably for preventing bugs and identifying undefined behavior. This talk is mainly based on the remarks from these, but as I said, this is not a talk about how you should start using them, but more about the typical suggestions they give and to turn them into a habit. But just to show you the static code analyzers that I've used for this talk are mainly ClangTidy and STPPcheck, both of which are free and open source. And so you can actually, if you want to, start using them today. The first part, inconsistency, is actually rather easy, so that's why I kind of made it into a quiz form, so you can quickly go through all of them very nicely. So imagine that you're the code reviewer and you receive this code, or you can also pretend, if you like, to be a static code analyzer. What would your remark be? Indeed, so ClangTidy will indeed say exactly that. So it's definitely, well, a consistency thing here, because, well, it's basically doing the same for this example, only using actually has two main advantages. The first one being that when I'm using Typedef, I constantly am forgetting what is the type and the actually alias type that I'm going to define. So I always have to search another Typedef and look at it to find out, which is not the case for using, because it's basically an assignment which basically automatically points out what is the alias type and what is the actual type here. And the second advantage is that for a Typedef, if you want to Typedef a template, then you are actually obliged to declare all the concrete types there in the Typedef, while for using you can actually leave them to be defined later on. And so as a result, on the long term, you see just using everywhere, because it's just generic usage, will actually turn into more consistent code. Okay, next quiz. Is any idea? So what we actually see is actually quite a lot of boilerplate here, and also quite a lot of repetition. And so the static code analyzer actually points out one of the two. In this case, it's basically suggesting that instead of having all those initializers here, to basically default initialize the members there. We can do that rather easily like this with just direct initialization, and we see there's already a lot less repetition, but there's still some boilerplate though. So there's also the other road we can take and actually try to reduce the boilerplate by using actually delegating constructors. This way there's less boilerplate. It's also significantly better than the original code, but you see that the repetition here is actually kind of back. So at the moment I think that's more a way of choosing and this kind of style that you want to take in that particular application. Okay, next one, an easy one. Here there is actually twice the same error. Anyone? No, it's already a ring. Reach-based forum. So the remark is actually to use an STL algorithm here. And actually, it's actually only catching on this one, but there are actually two in it, because here, where we are basically generating new values, we can also use an STL algorithm. So the end result is basically this. I know there already have been quite a lot of talks already telling you to use STL algorithms, but when I look at quite some code reviews that pass by me, then I see that actually a lot of people are still not using them. And what surprised me the most actually when I started using static code analyzers is that they're actually these algorithms are much more generic than it looks like when you start just reading their description on the algorithm library. For example, the any of or the all of that is actually suggesting, like here, this is a very simple case where it's quite obvious, but in almost all the for loops where I had an early return, I can write it in one form or another using any of or std all of. And then perhaps another one. So yeah, once again, we actually see a lot of boilerplate that basically shouldn't be there, because basically what we're trying to do, this is C++03 code, where we're trying to basically delete the copy assignment and copy constructor, and typically we make it visibly only privately, so that we actually get a compile error, and typically we also only declare them and don't define them, just to be clear. But of course, in C++11, we have the equals default and the equals delete keyword, which basically means that if we take the copy constructor and we put it in the public visibility and we do it equals delete, it actually allows the compiler to generate a much nicer error code. And it has the additional advantage actually that where in the C++03 case, once we start using this class and, for example, we start adding a member, then quite often people actually forget to adapt the other functions, of which we're kind of used that they're also automatically generated in other cases, and as such we actually have a potential bug here in the future. By simply using the equals default, the compiler is basically always generating them for us, and even if we change a member variable or add one, then it's basically still doing the right thing. So, okay, so far quite some easy things. We probably know most of them already. So let's take a look actually at performance. And what we see here is basically how we initialize a class, certainly in C++03, and it's a paradigm that's widely used by many developers, I guess, and quite a lot in a program. So basically, there's a const reference here, basically to avoid a copy, because by taking the type by reference and only copying it here, we basically get our type initialized here. Now, when we purely look at the declaration of this constructor, we see that while it's actually a widely known pattern, it's not exactly ideal. First of all, we need to be really const correct. If we're not const correct, then actually the caller of this constructor, it simply doesn't know what has happened to the object it actually passes in here. So it means we could have changed it even if we are not changing it today, we may be changing it tomorrow. So that actually means that when a programmer is actually using the example class, he or she has to keep all those things in the back of his or her head, and as a result, it gets actually much more likely to write a bug. Even if we are const correct, then it's still not a perfect solution either, because we're still having a const reference here, and without actually reading the private members, we don't really know whether it's copying it, like in this case, or if it's keeping a const reference to the original one, in which case the caller actually needs to somehow manage the lifetime of this type to be sure to be at least as long as the lifetime of the newly created type. So the static code analyzer actually warns for this, and we can actually fix it by basically requiring to be passed by value, and then basically moving the type. Of course, this is only a good solution if move is actually cheap, otherwise it can actually get more expensive. So in this case, just from an architectural point of view, this is actually already much nicer, because now we really have a type by value, which means that we can just pass a type in, and the caller doesn't need to concern himself with whether or not this class is actually doing anything with the type that was passed in. But of course, as we can see here, we're talking actually about performance, and if we start reading more about this remark, then we actually see that the real reason behind this is actually that we can somehow get more performant code. But to understand how that is possible, we need to take one more look actually at the old code. First, if we pass in an L value, then we basically get a reference to the L value. The L value is copied here into the type, and we basically are left with one copy. But imagine, for example, that we pass in an R value. This can happen rather easily. For example, if this is the return type of some other function that we directly put into the constructor. And in this case, the R value is actually first creating a copy in order to take a reference to it. Then we take the reference of that temporary variable, and we basically copy it once again into the member variable. As a result, we actually have two copies here in order to be able to initialize type properly. When we compare this actually with this case, if we pass in an L value, we're basically passing in by value, and at that moment we're basically moving the value into m_type, and as a result we have one copy. If there's an R value, we're once again going to create a temporary copy here before we are actually calling it, but now we are moving this one temporary value directly into our member variable, and as a result we once again have only one copy here. And we can actually measure this result rather well. So as you can see, on the left we have an L value, here for const by reference, here for pass by value with a move. We see it's quite similar. Then we see it's also very similar to actually using an R value with pass by value and move. And then we see that here the pass by reference with a copy of an R value indeed has significantly more cycles. Then we see that what the great news about this is actually that we basically retrieved our value semantics, which basically means that we're writing better code and that we don't have to keep all those things in the back of our heads. Now, when we're talking about value semantics, there's actually another nice thing that we can do. And take now this example where we basically want to retrieve a fills array. In your C++ 101 course, day one, you probably learned to actually write it like this. So we basically create our variable, we fill it, and we return it by value. Now, because they also learned this somewhere in the same course that this is returned by value, it's actually going to copy it into this one. And because that's suboptimal, it's actually they're probably going to tell you to basically create it here and then pass it by reference, fill it, and then suddenly the copy is no longer there. I also created a third one that actually generates this remark saying that here we are breaking copy elision. So perhaps in this example, perhaps people are not tempted to do it, but when things started to get more complex, some people might actually try to start moving it out, but of course this has actually little effect. But since it's talking about copy elision, that sounds like something interesting to dive into, right? Because for some reason it's not showing it here. And to be able to understand what copy elision actually does, we have to it's actually an optimization that is, which actually allows the compiler to, under very specific conditions, which are actually fulfilled here, to actually construct the returned value not first here as a temporary with a copy, but actually to automatically create it in the memory of the caller. So that means that actually this statement, using copy elision, actually is going to, the fill is actually going to work directly on the memory taken by copies and not by the result here. This optimization can actually not be underestimated, because even in C++03, there was already a very explicit exception allowing copy elision. And it's actually quite a particular exception, because it's one of the very few exceptions in the C++ standard library where it is allowed for an optimization to actually omit certain side effects that can occur. Because, for example, here we do a copy, and so say that the copy constructor has some side effects, then well, by allowing copy elision, we're basically not executing these side effects when we apply it. And so, this is quite a significant optimization, really. And so, if we actually measure it, we see that indeed it can be elided. So we see copy is here, similar performance as referenced. Technically spoken, it's even slightly faster because it has to do less work. But I don't expect anyone to actually really be able to measure it, certainly not in benchmarks that are rather noisy in this regard. And we also see that if we have actually blocked copy elision, that it's actually slower than the actual fastest case. And so as such, we actually see that once again, actually the thing we learned in our C++ 101 course, day one, is probably the optimal solution here, because it's the fastest one and also the most safest and more clearest one to use. Okay, so now let's go to the part where we're actually trying to detect bugs, and that's what typically static code analyzers are used for. And there we actually have this program. It's basically, we have like a devices class here, and for some reason there's an optimization, because all devices, they have the same maximum number of devices that they exist actually there, and so we made it a static. The static is actually initialized by a function that basically gets the number of devices and initializes it, but in certain cases this number of devices can actually throw an error. Then in our main, we basically have a very generic catch clause that you see actually in a lot of production applications, where basically any exception that for some reason is not caught somewhere down below is actually caught very generically. We basically catch it very gracefully, and we still return success. But if we actually execute this code, we actually see, first of all, we see that the exception is indeed thrown. But we see that it was not actually handled gracefully, and we have a crash here. So to understand what's happening here, we actually have to dive a bit under the hood. And in this case, we have to look at what actually happens between the kernel that is starting your program and the actual calling of main. And it does only a few steps there. First of all, it's going to initialize your the text memory of your program memory layout, which is typically just a copy of all the strings, which always have a static visibility from your executable into the your memory layout. Your .data, which is basically the static and global variables that are initialized, that are basically called here and initialized. And may or may not also be copied from your executable depending on how it is initialized, or it may be called a function. And then there is the BSS, which is also the global and static variables, but the uninitialized ones. Only then, also of course the stack is initialized, and then only then main is called. And now we see, because the device is actually a static variable, that is actually initialized here. And as a result, main is not called yet, so if we throw here in this stage, then basically there's no way we can actually catch that error and do something with it. This is a problem that's actually quite often overlooked. It's kind of in the same category as new that can actually return a null pointer, which is basically ignored. But I think that in high quality code, it's actually important that those things cannot happen. And indeed, in practice, sometimes these things happen. Of course, this was a very explicit example, but they can also be much more subtle. For example, here. Does anyone know why it's actually telling us this here? Okay, so it actually turns out that this string constructor can actually throw in certain circumstances. And it can throw in case that this string is actually longer than a certain maximum allowed length of the string. Of course, on most targets that will be absolutely no problem for such a short string, but it can happen, and the static code analyzer is actually warning us for us. In order to prevent this kind of crashes, actually, you have in the generic case, there are three options that you can do to fix it. First of all, we could make a variant of this constructor that does not throw, but that basically means that we have to re-implement std string, and that we suddenly do not have a std string that is compliant with the standard anymore. So that's not really an ideal solution here. Secondly, we can actually wrap it in a string wrapper that is actually no except when it gets initialized, which basically means that we should catch this error and handle it gracefully. Also not exactly ideal to work on in the rest of our program, just to fix this issue. And thirdly, we can actually try to lazy initialize a value, which is probably a good solution for our first example with the devices, but obviously for strings also not an option. So it looks like we kind of have a problem here with string. Luckily, this has already been solved for us in quite another way. So first of all, if you're lucky enough to use C++17, then you basically can just use string view and you're okay. In case you're not working with C++17, you can actually use C-style strings because, well, C-style strings, they don't throw. But because that's not really a very convenient C-style string, and we don't use them these days, of course, the GSL actually provides a string wrappers specifically for constant C-style strings, which kind of already improves the situation a bit, but still is not ideal. Then another particular error. So basically what we have is we have a base class, and there is a derived class here. Then we have just one function that is basically just copy assigning a derived class to the base class we actually pass in. And then we basically have another derived class that actually calls that function. Now when we print out the member variables, we would expect them to both be 2. And in particular, that foo and foobar will be equal since, well, they're basically both initialized in the same value and we're basically not doing anything else with them. Unfortunately, when we actually run it, we see that they are not the same at all. This is actually known as object slicing. And so to really understand what's going on here, we basically need to get behind the scenes. More specifically, we zoom in actually on this base class, because this base class, while it is very shortly written here, there is actually at the background a couple of things going on. Of course, the move constructor and the move assignment operator are not automatically generated here, but the other ones are. So when we actually try to copy assign a derived class, basically it's trying to find in the base class a copy assignment that takes the child overload. It's not going to find that in base in this case. So if there is a miss, then the compiler is going to look at a copy assignment that's actually taking a base, which it does find, and so it actually calls that function. But in this copy assignment, we kind of have a problem, right? Because we have two base classes, two objects of which we only know that they are of type base. So we can copy foobar, but there is no way to get a handle on foo or to even know that we need to copy foo at all because it's something in a derived type. And of course, at this point, we have no idea what our derived types are or who's even deriving from us. And so it's not copied there. Just to be clear, even if we would actually add a copy assignment override here, it still wouldn't fix the problem, because then we have one child object from which we can take foo, but the target object still has no way to actually get to foo, because we don't know what the specific derived type is. And of course, that's kind of bad design probably if we start putting derived classes in our base class. And so that's the reason why only foobar is copied. And so luckily, if you're lucky, we have a static code analyzer which actually warns us about this these days, and so we're good. The bad news is actually that, unfortunately, that when you do this like with code reviews and you don't have a static code analyzer, then most likely your other people are not going to catch this error, because it's rather subtle in here. The good news is actually that there is actually a solution to this problem to make this a compile time thing, and that's actually by applying a rule that we all know, only in quite a different context, and that's basically the rule of 3 or 5 in C++11, which we also get actually a static code analyzer remark for in case that we're not following it. So the context of the rule of 3 is typically quite different. It's where we try to manage our resource, and it basically tells us that if we either define a destructor or a copy or a move constructor or a copy or move assignment, we should always define all the other ones too. So basically like this. And for resource management, that seems to be working quite well. But of course, we're here in the objects. We're basically here just inheriting. There's no resource being managed here. But we do have this virtual destructor here. So that bears really the question, do we need to apply the rule of 3 here or not? And well, it turns out that if we actually do apply it here, basically meaning that we will define all the other ones here, we will put them in protected in this case, because the base class is not supposed to be actually used really as a concrete type. In which case, we basically, if we try to use any of these functions, we're basically going to get a compiler error because it's simply not visible from outside. And so this way we get a compilation error at the moment that we're actually trying to do object slicing, at least for base classes that are not supposed to have a specific type. So apparently I went quite fast in this. What can we conclude from all of this? First of all, there are quite some things that we can actually put into our muscle memory. We also see that with newer standards, a lot of new things are added, and in addition, there are quite a lot of things that are actually worthwhile to be put into our muscle memory. We also see that those habits can span actually multiple areas, so it's definitely worthwhile for everyone to basically invest in them and to learn a couple of them. We also don't need any static code analyzer to actually start applying them. We can start right away. And yeah, the last conclusion perhaps is it really pays off to start using a static code analyzer. Okay, thank you for your attention. And I'm open for questions.
Hi, thanks for the talk. Would you recommend in our CI systems those checks should fail the build? And do you do that?
Yes, I definitely think you should. So I tried to do it in as many projects as I can, actually. Unfortunately, it's not always as easy to do so. Certainly in existing code bases, it is not always easy to start introducing one because there will be a lot of remarks, and you don't even typically see the new remarks in between all the old ones. So that's typically a build-up and something that needs more work to actually start doing it. But definitely, certainly in new parts of code, it's definitely recommended to start doing it, yes. And to also regularly check it using CI systems. Yeah.
Do you use clonk tidy and CPP checker, or just one?
In my hobby projects, where I typically work actually as a single developer and I have no one basically looking together with me, I am tempted to actually use quite a lot of them. Actually, I have this one hobby project where that's just basically my playground, and there I actually try to implement as many or use as many of those static code analyzers as I can, and just to compare all of them. And there, so there I use a lot of them, and you see that where some have like a gap, others can really fill it in, and then you can start really comparing it. I think in practice, for non-toy projects, and probably starting with one is probably already a good thing. And then there you see that there's quite some difference actually between quite a lot of static code analyzers. And clonk tidy in particular, in my experience, is very good at catching most of the issues. Okay. So no further questions, and thank you for your attention.